Hello, everyone. It's a pleasure to be here to introduce to you our speaker, our very distinguished speaker today, Dr. Vaishak Belle. Vaishak is a Chancellor Fellow and Faculty at the School of Informatics, Edinburgh. A place that has a long tradition in artificial intelligence. He's a professor there working for artificial intelligence in a variety of issues. I think all of you got his short view, which is not so short. It's already quite long. Without further ado, I'll call Vaishak, and please, the floor is yours. Thank you.
Thanks, Fabio. Is this good? Thanks again for the hospitality and having me here. So I'll get started with the slides. The slide title, as you can see, is a bit long. Is that coming up? Yeah, good. So mainly it's long because it has a couple of different parts. I'll mention a few connections at the end about how they all relate to each other. But I think for the interest of this talk, it's not necessary to make the connection, right at the start. So we move on to the next slide. So as the title says, this talk is about explainability. And I got into this area in about just before the pandemic, in fact. I was having some discussions with NatWest Group, which is a big banking institution in the UK. And one of the things we were wondering was, there's all of this excitement around explainability. So DARPA had come out with this huge explainability initiative in 2016 or 2017. And we were wondering, what would all of this mean in a more commercial context? And what we ended up doing was trying to provide a bird's eye view of what explainability is, what it's achieving to do, and also predicate this by saying that it has changed over the last 2 years. It's become quite a bit more complex, has a lot of different parts, but I'll mention that briefly. And the second part of this talk, I talk about an area that is closer to my research interest, which is on logic and its connection to learning, which includes, has now come to include something called neurosymbolic learning. Mention briefly about that and provide some connecting threads on the two bits. So if you move on to the next slide. So let's just take a step back and think about what explainability is all about. Next slide. So as many of you might be aware or you might have heard of, it's an area of research that's coming up with a set of tools that's trying to make the decision boundary sensible or interpretable or readable, however you want to call it. And again, that matters a lot because each community is taking that notion and running with it in a way that fits them, which is fine, right? Because you want the area to develop in a kind of organic way. So it's a set of tools that's trying to provide some kind of perspective on what the decision boundary is. And you want this in a way that ideally doesn't affect its effectiveness. So you want the system to work just as it did before, but now you have this additional interface or layer that's providing some clarity on what's going on. Okay, so that's the broad game here. And I say that there are two terms that often come up in the literature, and for the most parts, these terms end up getting used interchangeably. So people don't make a distinction, but I think there are these two definitions that, to me at least, make a lot of sense. Is to see explainability as a kind of active characteristic. So this is an actual thing that you need to provide as a kind of interface between the human and the system, to provide some kind of communication back and forth between the two. Whereas interpretability is more passive, okay? So it provides a perspective or an insight into what is happening, but it's up to you, and presumably you're an expert or a scientist who understands the mathematics or whatever it is, and you're able to understand because of your background knowledge and your expertise. Is it better that I'm here, or? Yeah, sorry. It's because of your expertise and your background that you're able to make sense of it. Okay, so these are two distinctions. Again, they are soft distinctions. There's lots of work on crossover, but I think it's nice to have these two distinctions. If you move on to the next slide. So philosophically, right, explanations have been something that we've been thinking about for as long as we've been talking about language. And it's always about communication. So ideally, if you think about an explanation between you and me, it's always to fill a gap. For instance, your question might be, why am I here today? And in that question, you're asking me something that you do not know and you want me to answer. And the right response there wouldn't make sense to tell you what I wore today, but the exact set of reasons that got me here, right? So we're trying to fill a gap. Explanations are about communicating relevant knowledge. And because artificial intelligence encompasses machine learning as one of its bits, it turns out that explanation as well has meant different things to different communities. So, for instance, there are good arguments now that explanation should ideally encompass some amount of planning, by which I am trying to provide some kind of justification in a set of sequence of actions that are taken to do something. There's obviously HCI elements, right? Because I'm having an interface between a human and a computer, so there's HCI elements to it. So it encompasses, I think, as a consequence of this broad definition of explanation, it encompasses many different technical devices, right? So there's interactivity, there's causal attribution. So an explanation as to why the glass fell on the floor when I pushed it is a causal attribution because I pushed it. There is also debugging, right? So an explanation could tell you why something went wrong. So there's a debugging aspect to it. You can inspect the decision boundary. So for instance, you might be curious to learn, and this is something I talk about in my slide deck, as to why exactly the boundary responds in one way or another. And finally, there is mental state modeling, which I think is a very nice kind of dimension to explanation, where there is an active characteristic by the system to try and understand what the human is asking, right? It encompasses all of this. If you move to the next slide, I, for the interest of time, I'll only focus on understanding the decision boundary. Okay, so there's a couple of good reasons why even focusing on this narrow aspect is interesting. Whether we like it or not, as much as we understand that there are more complex hybrid machine learning models and AI models we can build, in some sense, the majority of machine learning systems we see out there are kind of the one-shot classification type approaches. And in this case, it does make sense to understand how they work, right? And if you're trying to have some kind of link between a low-level machine learning system and a high-level reasoning system, you still need to figure out what the low-level system is doing. So even this very kind of isolated aspect still is quite interesting. It still gives you some perspective of what could be done to understand the robustness and the stability of the model. So there's a lot to learn even in this. And as I said, the second part will be on the logical aspect. This is about structuring domains. In the interest of simplicity, I'll abbreviate the whole thing as XAI anyway. Okay, so even though, as I said, XAI encompasses all of these complex dimensions, just in the interest of simplicity, I just call it XAI. Okay, let's move on to the next slide. Yeah, if you move on. So the culprit here, right, is this idea of a black box machine learning model. So what's happening here? The way any of these systems, regardless of whether you're interested in deep learning or support vector machines or whatever it might be, the key thing here is that you're presumably given a bunch of data points which provide you training data. You have some sort of label or target to these data points, and you're trying to construct this function, right? You're trying to approximate presumably the function that takes this data point and gives you the label, right? And now there's a couple of things happening here. For instance, you want to emphasize that there is good generalization, which means that when you get data points that are in some sense similar to the ones you have seen, it behaves in an expected way. And that's kind of, a thorny area, right? There are theoretical approaches to look at generalization bounds, but in most pragmatic settings, I would say people just assume that if you train it on images of cats, you provide a new cat image, it should do the right thing, right? So there is an implicit assumption that the generalization bound does what it's supposed to do. And again, the problem here is that we are attaching a semantic value to these data points, which the algorithm may not pick up on, right? And that's essentially one of the key problems, because we train it thinking it's supposed to be doing this, but it's really picked up something else, and then it basically doesn't perform. The next slide. So all of this came up in very stark kind of shock in 2015, where people started looking at the robustness of vision systems, for instance, that were trained as black box systems. And here's an example where the first image, which is obviously a panda, but as you notice, it's only with a 60% confidence. You add the small amount of noise, right, and now the system thinks it's a kind of monkey with a very high confidence, right? And you can think of this kind of system being in a self-driving car, and it does a silly mistake like this, and it could cost lives, right? It's not just in vision. So there are also examples in language where picking up statistical similarities mean that it does silly things when you ask it something that matters, right? So we all have to be cautious about the fact that black box systems are black box in the sense that you really cannot interpret what the system is doing just by looking at the architecture or the hyperparameters or whatever. So that's the essence of the so-called black box system. So what else can go wrong, right? Another issue, it goes back to the point I was saying, the first issue is the fact that you can have wrong objectives. So again, you have a semantic attachment to your data points, and you presume that when you train the system picks up on the semantic attachment. So it gets images of cats, and you think it's picking up the shape of a cat or the whiskers of the cat or whatever, but it might be picking up on something entirely different. So you could have, a kind of mismatch in this regard. And again, the mistake could be entirely innocent, or it could be that you do not have a way to understand the high dimensional space, and so you make a mistake just by accident, right? The feature space may be inadequate. What does that mean? Maybe it's a very pixelated image, maybe the lighting conditions are off, or maybe the abstraction from the data points to the features is too hard to make sense of. And this could mean that you could train an algorithm that is biased, even though you have taken some effort to remove the bias, right? So all of the feature space can be very complex, and it's really hard to really figure out in high dimensional data what exactly is going wrong. If you go, I think we missed, yeah. The third point here is that there is this issue of distribution bias, or distribution drift really, is the fact that you train it on something, you go and test it on something else, and there's a difference in how the real world data point looks like compared to the training data point, and you could get funny results, right? If you go to the next slide now. There's all of these issues about user acceptance, user control. You want to debug, you want to improve, you want to understand how it can be improved. So all of these are big factors. And finally, there are legal imperatives like GDPR, which mean that you might be audited for deploying an algorithm that affects people, and then you have to come back and justify why something was taken or not, why a certain decision was taken. All right, so this is just providing the landscape of black box ML and where things can go wrong. So let's think about who's benefiting from explanations. Okay, and this is just a prototypical example. So it's not a real world scenario, but although there are many parallels with how things happen in banks and so on, the key stakeholders here is typically have a data scientist who's trying to understand and debug and improve the model. You might have a business owner who's trying to figure out, is this good for my business? Is it improving sales, etc., etc. You might have a model risk analyst who's looking at, is this, playing with my treasury or my resources in a very dangerous way and potentially causing harm, long-term harm. You have regulators who check on impact on consumers, and then you have the consumer himself, right? Who might ask, what is the impact of the algorithm on me? Now, one thing to keep in mind, if you go back, one thing to keep in mind is that the consumer, in a way, there is assumptions here that the consumer can still make sense of the explanation, right? Which may not always be the case. And this can lead to some issues even with legal imperatives, because you could suggest the explanation in a way that is truthful, but still not informative enough for the consumer to act on it. So if those things happen, the consumer can walk away thinking they have an explanation, but they don't really have an actionable explanation. right? Or they don't know how to act on the explanation. So there is quite a bit of complexity when it comes to the consumer and explanations, because there are certain assumptions you have to make about how much the consumer understands about the model. Okay. So what I'll try and do now is do a couple of things. I'll try and tell you. So given that we have a need for explanations, where do machine learning models sit? Where do explanations sit? And what type of explanations are interesting, right? As a first step, and not obviously I won't be able to cover all the explanations in the literature, but at least it'll give you an idea where things fit, okay? So one criteria that comes up when in machine learning models is this distinction between so-called transparent and opaque. And again, this is a kind of a soft distinction. In some ways, it does make sense. So, for instance, there are some qualitative criteria you can provide on things like decision trees, which is the idea that it can simulate the model in your head. For instance, if I'm deciding whether I take an umbrella today, there is a certain, kind of if-then-else logic to it. If it's raining outside, or if my weather app is saying that it's going to rain, I'm going to take my umbrella. So there is a certain logic to it, and so it does become transparent because you can simulate the solution in your head. But the danger is that if you think about a tree with thousands of nodes, it no longer makes sense to you or me, right? Transparent models are clearly have a certain transparency feature, but it is not always the case that with big data training you will get transparency just because the models are transparent, and that's a danger, right? So the nice thing here is that there are the explainability techniques work just as well with opaque models as they do with transparent models. So you can basically apply them, most of them at least, to both transparent and opaque models. So this brings me to this idea of post-hoc explainability, which is a set of tools again, where they take a trained model and try to do something with it so that you can understand what's happening with the model. And there are a couple of different things to this. There is this idea of what is called as a model agnostic versus model specific. And what that means is that, are you building a tool that is exploiting the architecture of the model, or is it just general purpose, right? There is local versus global, and this is actually a very key distinction. So local explanations look at the data point you care about and around that region, whereas the global one is looking at the entire decision boundary. And the thing is that often local explanations look very attractive. They look like something that's actionable, but it might be because the space is so big, something might get lost, right? You may not understand the overall logic by looking at a local point. And of course, explanations can be many things, right? It can be textual, it can be a long conversation, it can be a story, visual, whatever, right? So I won't talk so much about the types of explanations, but I'll focus mainly on these model specific and model agnostic, local and global. One of the things we did in this work was trying to come up with a taxonomy. This was inspired by some earlier work. Trying to come up with a taxonomy for where explanations sit. So I'm not going to spend time on every block, but roughly you have transparent and opaque models, right? Transparent models have things like decision trees. Both of them you can plug in post-hoc explainability with. And here again, you have model agnostic versus model specific, and there are various techniques that come up. Okay, so it's just a way for you to navigate it, but we'll see more clearly how this plays out. By the way, how much time do I have, Fabio?
Oh, should maybe 45 minutes total.
Yeah.
So take time.
All right, so to see where these techniques fit, I'll get into that in a second, but I want to mention one thing that became very popular, and I think it's still popular on social media and so on, is this idea that techniques like deep learning are better at everything, and also the fact that they are low on explainability, but some other techniques are low on prediction accuracy but high on explainability. Okay, first thing to note is that this is not a real plot, right? I mean, it's obviously it was not generated from a single data set. We have no way to quantify explainability. So this is a kind of folk idea of what, where techniques fit in. And it's not really true, okay? So certainly with certain kinds of data sets, it is the case that deep learning techniques are providing perhaps the best and most promising results on those benchmarks. But as soon as you have structured data and you have knowledge, often it becomes quite hard to incorporate them. So, this plot shouldn't really be taken at face value, right? So we don't really know what the next best machine learning system would look like. And, just because deep learning systems are by construction opaque and decision trees are by construction transparent, it doesn't really mean that they have this kind of explainability comparison or that one outperforms the other in everything. So yeah, anyway, this is just a misconception that often comes up. So how do you go about it and which technique to apply, right? So as I mentioned, there are a whole bunch of different techniques. And what I do is I try and give like a simple narrative that kind of shows where things might fit in. Obviously, this is not an exact science. That there is a lot of literature out there on what techniques work for which domains, etc., etc. So this is just a way for you to help you think where things might fit in. Okay, so let's consider again a very simple example where you have something like loan decisioning, right? So you apply for a loan, do I reject it or do I approve it? And I'm acting as the bank. And one very common thing that you might think is the data scientist might come back to the stakeholder and say, why don't I give you some feature relevance charts? Okay, so let me plot different attributes for my data points like salary, age, family size, mortgage, other loans, etc. Let me map them out. And there are certain red and blue bars. I won't have the time to go into that, but basically they compute the contribution of that attribute to the overall decision. Okay, so it's a bit like in a game theory context, it corresponds to a payoff. It's if you have different players playing a game, how much has each person contributed to the overall result? Okay, so this is a popular technique called SHAP. So this is one approach, but you could come back with a question that says, imagine this is COVID and salaries start to decline. What can you tell me about that? Okay, you go to the next slide. In this case, you can come up with what are called as PDP and ICE plots. And what they do is that they look at the probability of approval as income is fixed. Okay, so income on the x-axis, and you're looking at probability of approval on the y-axis. But you could also do this at an instance level. Okay, so you can plot all the instances in your data set, and you can see for the majority of data points, a certain behavior holds. Okay, so you can see, for instance, where or how much the salary matters to the overall decision, right? So in this case, the stakeholder might say, okay, this is great. Can you tell me specifically for a certain individual, let's call this person Mr. X, okay? Now, what you're able to do with the technique called counterfactuals, which is a local method, by the way, is that you're able to take that data point and you're able to change certain attributes to see what happens to the decision. So you're really kind of visualizing the decision boundary. So you're going to say, if I decrease the income by 50%, I'm going to reject this person. If I decrease it only by 25%, I'm going to approve. If I decrease it by 25% and this person missed the loan payment for some month, then again, I need to reject him because he's not a reliable mortgage holder or loan holder or whatever else. Okay? So counterfactuals gives you that perspective of toggling certain values in the data point and telling you what's happening. What you could also do differently is to come up with rules that tell you how the features behave. So again, here you might see that as long as the income is greater than 20,000, then you accept. If it's less than or equal to 20,000, you reject. So you can. So yeah, this is a technical anchor that comes up with rules to tell you how the boundary works. I think there's one more slide. Right. Another way to look at the decision boundary is that you could, it's a technique called deletion diagnostics, and it makes a lot of sense. It's basically about what would happen if I drop the data point, how much would the decision boundary change, right? And you see that if you drop this person, the decision boundary still remains roughly the same. So, this tells you about the robustness of the model, right? So this is another popular way to inspect the, the sensitivity of the model's decision. And finally, there is a global rule. So all of these were local. There's a global rule that kind of looks at the overall decision boundary and again comes up with rules for it. Okay. So if you go to the next slide here, what you see is that you can basically look at the kinds of questions you want to ask about your model, and I think in most circumstances you might be able to pair this up with some technique. So for instance, you might be able to try out inference and chat, as I mentioned. You might be able to talk about, if you remove the data point to deletion diagnostics, there's a way to tie up different questions to different explanation techniques. So I think the key takeaway here is that depending on what you want to do with the model, there is a way to navigate the different techniques and find a corresponding technique that kind of owns up to your kind of question you're interested in, right? So this is a way to kind of navigate this. We've done 2 follow-up pieces of work on this. We have developed a kind of a course based on this, where we kind of look at, not only at the high level, but also we go into the depth of different explanation techniques and to tell you how exactly you can think about explainability. How can you connect your way of thinking about the model to certain questions and so on. Anyway, if you're interested, they are available on the website. So we've done a couple of different things taking up from here. I think I have another 10 more minutes, so I can tell you about the second part of the talk, and I will connect back to the first part of the talk, essentially. The key insight that people, I think many people in this room as well, have been arguing for is that one thing we notice about machine learning is that it's good for inductive generalization. It works on big data, right? But it often treats all of the data points as independent and identically distributed. But often, this data is not coming in the abstract. It is coming in a specific context. There are some domain constraints, there are some relations, and so on. And this brings us to the need to kind of integrate certain kinds of characteristics in this overall picture, right? So you might often need to do reasoning. So for instance, a common example right now in the machine learning community is you might have so-called visual QAs, right? So you have images and you have certain descriptions below that, and you need to tie the descriptions to the images and figure something out, right? So sometimes you need to do reasoning. You might have hard and soft constraints. So for instance, you might know that in a physical domain, so for instance, if you're doing something with motion dynamics, certain laws hold and certain things potentially hold. So you need to deal with hard and soft constraints. You need relations and objects, and you need to go beyond association, right? So association only gets you so far in coming up with a picture of the world. You really need to have a mechanism to connect certain actions to certain effects. And that won't be possible simply by feeding in data and getting some labeled output, right? So you need to do some extra work to actually get this out. So this kind of brings this picture on trying to have structured knowledge as part of the machine learning process. I think, Fabi, you have work on that called knowledge-enhanced machine learning, which I think is in very similar spirit. So what I do over the next couple of slides is give you a few examples of what we've done on that. To kind of show you that this is not just an abstract mathematical principle, but it really makes a lot of sense in practice. It is, if you look even at something like protein expression, right? You find that there are clearly interactions between genes and proteins based on various characteristics. There's often a probabilistic dependency between them. So if you go to the next slide, for instance, the kinds of questions you're often interested in, is gene X involved in some disease? What is the probability of involvement, et cetera, what happens when you condition, what happens if you intervene? There are all of these interesting medical questions you need to ask. So it's not just an abstract thing, right? And if you just train a system that simply plots what the next data point's label looks like, it's not going to give you enough information for this kind of stuff. And one thing you notice now is that this kind of structure, which is really just a graph with probabilistic nodes, kind of looks very much like a structure we have been studying in computer science since 1970s, right? It's mainly that you have nodes, you have arcs between nodes, and you have certain probabilities of pathways, right? And this can be captured quite simply with the kind of program like this. It's not the only way to write it. There are many other ways, but it's still a fairly compact program. And the key thing to notice here is that the definition of a path, which is that X and Y are connected by an edge, or there's one thing connecting to another edge, is a general constraint. So the only thing that differs here are these data points, right? So you could have a graph of arbitrary size, arbitrary complexity. You feed in these data points, but the path constraint and the kind of reasoning you might do is general purpose, right? So that's the power of this. So there's an abstraction and a separation from the computational aspects from the data aspects, and this provides a nice elegance to doing problems in this space. So this brings us to the science of logic and probability, right? So the need to really combine signal processing and machine learning. Okay. One of the kind of key insights that's happened in sort of the, let's say, the community at the intersection of machine learning and symbolic logic is that there is a kind of commonality here. When you look at the computational graph, you look at the program, you look at certain data structures that can write this graph or this program compactly, they all look like what I call as probabilistic logical formulas. Okay? Now there are various complexities to this. For instance, these symbols here could be continuous, they could be discrete, they could be coming from a neural network, and just as you change the different parameters of these ingredients, you come up with different disciplines within artificial intelligence, right? So it's a really powerful abstraction to help you think about problem solving. I'll give two possible applications in language and vision, and of course, I'm sure there are many. This is just work that I'm familiar with that we were involved in. In the language case, right, the kind of thing we were thinking about is if you have combinatorial problems and probability problems that you see in high school, like this one. This says that Mike has a bag of marbles with 4 white, 8 blue, and 6 red. Okay, he pulls out one marble from the bag and it's red. And what's the probability that the second marble he pulls out is white? Okay, so what's happening? You have a probabilistic model at the top. You have some kind of conditioning, right? And then you have a query at the bottom, right? So these problems obviously look a lot like these probabilistic programs. In fact, we can show, you go to the next slide, that there's a nice translation from the natural language to a kind of abstract syntax, to then the program, and you run the program and it gives back the solution to the question, right? So there's a nice kind of loop here where reasoning is done in the program, there's natural language processing done in the extraction of the syntax, right? So there is a place for conventional machine learning technology to fit alongside reasoning, right? If you go to the next one. The other kind of thing we have been looking at a lot recently is functional reasoning, right? So essentially, if you look at any vision paper, it's very common to have these massive data sets with digits and animals and cats and dogs and trucks and whatnot. But clearly, when we look at images, right, we are doing things with it. We are functionally reasoning about it, right? So I might see a logo, and I might start connecting it to concepts, right? So, for instance, in this case, you see this image here, right? And what I'm asking you is that based on this image, what is the second image such that when I take the XOR function between the two images, I get a 1, okay? So if you're not familiar with this, XOR between two values is only true when they're opposites, right? So 1 XOR 1 will give you 0. It's only when they're opposites. So indeed, when you provide, these images here, the system spits back the corresponding solution, right? So in this case, it's all ones, whereas here it will give you a 0 and then 1 in these cases, right? Similarly, you might think about image recognition, but no longer the classic style where you give the labels to each of the images, but instead imagine you write some text on a piece of paper and you give the interpretation of this text, but not the interpretation of the individual symbols, right? So this is really powerful, right? So in this case, for instance, I'm providing these images. I'm not giving the label for this. All I'm saying is I'm going to add this one to this one. I get a 2-digit number where the first digit is a 0 and the second digit is a 3, right? And so the system has to figure out purely from the right-hand side what these digits might mean. So it's in a way it's a label-free supervision, right? So you're not giving the label to the actual images. So there are 2 ways of doing this. I'm not going to go into the details, but just to give you the idea. So one approach we take is we take the data, okay, we project the feature space into a logical program, which kind of makes sense, right? Because the logical program now starts interpreting the features. And if you construct this logical program to reflect whatever logical function you want, it will do the behavior for you, right? So this basically, we're outsourcing the logical reasoning to this external thing, right? And so basically, we do this with what is called an auto encoder, which means that you encode the data in this kind of structure, you decode it back, and it gives you the output. Okay, so this is one approach that we have. Another approach we have is, which has become really popular now, is to tweak the loss function of the deep learning system. Oh, I have another minute. So what's the idea here? Let's look at this equation here. I don't want you to spend too much time on it, but let me just try and make sense of this for you. Okay, so what it's saying is that there are some sequence of labels for the first image and the second image. I'm not giving that. But what I am giving is the label for the third image and the label for the fourth image, right? So if you go back to 2 slides earlier, this one. So I'm giving the label for this one, and I'm giving the label for this one. So basically I construct this as a kind of logical formula, and I feed it as a signal back to the neural network, okay? It can go back now. No, the next one. Right, and so this is another approach that also captures this kind of functional reasoning. I mean, I have to say that there are many other approaches that are similar in spirit, and so this is kind of an interesting area right now. I would say its applicability is still kind of curtailed by certain toy problems, but still I think it's a logical flavor to deep learning. It's kind of has an interesting promise to it. All right. I'm not going to go into the details of this too much more, but there's a whole range of exciting problems in this space. For instance, one thing that we've been interested in for a long time is how do you learn those kinds of programs from data, right? So it's basically like, what you want to do is you want to give some data, you want to construct a very small program such that when you run the program, you can get the data back, right? So it's a bit like data compression, but in a programmatic format. So basically the program is telling you what the data is doing, right? So it's really powerful because it's a bit like you can read the machine learning decision system completely transparently, right? So we've been thinking a lot about learning programs or circuits or formulas, whatever your favorite flavor is for data. And then there's a completely different dimension to this, right? So for instance, I mentioned causality. So the question is, what would the integration of causality and this area look like? It can, still on that point, it can mean many different things. It can mean you have some kind of program and you want to causally inspect certain actions and their effects. It can mean that you are constructing the program by targetedly intervening on the data. So there are many dimensions to this, right? Likewise, going back to the first part of the talk, there is a lot of work now on trying to reconstruct the explanation generation system in a logical language. So you can compute things like consistent explanations and so on and so forth. So, I'm happy to talk about that at some other point. But the many topics that we can go on. All right, so to wrap things up, and I think I'm doing okay on time, is that explanation is a very challenging topic, right? It has many dimensions, many interesting dimensions, and I think a lot of people can contribute to it, from social sciences to philosophy to robotics and so on. I only looked at the interpretability aspect, which is, as I said, very limited, and the structured knowledge aspect, which is the second side to it. What I think most people agree is that the increasing prevalence of machine learning, you need to think about human in the loop, right? But the question here is, where does the human intervene, right? At which point is a human input necessary, and which point can we do with algorithms and computing, right? And that's, I think, the eternal computer science ideal, right? That we need to automate as much as we can, even if in principle we don't need to, right? We need to understand the limits of computation. What I certainly think is that regardless of whether you think these systems should be deployed in the public domain or not, we do need these systems to have contextual understanding, right? Because it is very likely that somebody who was using the system and is not an AI person will blindly trust the decision. So we should expect the system to have that level of understanding. And undeniably, this needs, I think, an integration of reasoning and learning. All right, thanks very much.
Thank you. So actually, we have time for questions before we go to the coffee. So please,
thank you very much, Vaishak, for your talk. In the part where you said where you look at the program, what's the explanation and what's the explain in this case? So, how do you frame the problem of explaining?
So a couple of different answers to that. So one, let's say, vanilla thing you could do is imagine you have certain data points that are labeled whatever, dog, cat. I don't want to use dog cat example all the time, but you get what I mean. They have certain labels. What you might have to do is to say that when the certain conditions hold in the body, that label is done. Right? So basically saying, if I see a ear that's triangular, if I see whiskers, then the label is a cat. So that could be one possible explanation, right? But the flip side of that is, so in this case, I'm constructing a program that explains the machine learning decision boundary. Conversely, we have a data generation program, which means that the program is a sample from the program, which means that it's a policy program and run through certain branches and so on, to get back to data, right? So in a way, it's a data compression approach. And the program is in some sense providing a compact information for what the data is seeing. Does that make sense? So in one case,
The second one makes more sense than the first thing.
yeah, I think the first one is still interesting. So one place where that's come up is people in reinforcement learning, right? So they're kind of interested in what does it mean to have an interpretable policy. And there's been some work where they basically show that, if certain conditions hold, then I will take some action. Which I mean, to me is an explanation, right? Because it's basically telling me the preconditions need to act in a certain way. So for instance, if I see there's a fire, I'm going to get out of the building, that kind of thing, right? So in that sense, the label is get out of the building or stay in the building or get some water or whatever it is. And in this case, the conditions of the body are telling you that the label holds, which is, I mean, as I said, RL policy setting, it kind of makes sense, in that sense.
Yeah, but the first one is trying to explain the machine learning, but there was no machine learning, it's just having data.
Oh, okay, so I just skipped that part. I mean, presumably, train a model that is doing the decision for you. And so what the program is trying to do is to look at the machine learning model and construct the conditions that you do.
Yeah, but they use the model was generated in some sense or not. That's it.
It did use it.
Or I lost it.
Yeah, we can take it offline, yeah.
So I think you have questions, remote questions. I don't know how you see them. is Maurício has to show them.
É o Fernando que está controlando aqui na sala.
Okay. So I have actually few technical, but let me start with a human question. So you have this taxonomy of explainable, interpretable systems. There's one thing that sort of bugs me about this explainable enterprise, which is you can always come up with some explanation for whatever you did, right? So there's a sort of, ethical question, right? You could always explain, even if it's something that's not related to anything at all. Did you think about this in your taxonomy?
Yeah, I exactly. I think, or at least I think I know what you're referring to. It's it goes back to the point of saying that I have a slide with the consumers, right? So in a way, an explanation can also be deceitful.
Yeah.
Without being false, right?
Right.
So, so no, that doesn't address that kind of subtlety, right? So I think the view I would have is that it's not meant to serve a context. It genuinely, you as a data scientist, is asking yourself, what is what I'm doing, right? And so you think about this deletion diagnostics, contractions, whatever, they help you probe. I mean, to some extent, it is a black box. So again, as I said, contractions are local, so you don't really know if it's globally, whatever. But still, it gives you some perspective. So from the perspective of a curious data scientist wanting to make sense of her model, the taxonomy is useful. But if you come to that view of these aspects of a passive, active, or withholding information in an explanation, as I said, it could be truthful, but withhold it in a way that could give the positive impression there's no hope here, or whatever, right? I mean, that's always possible to do. Then, yeah, it's obviously benefiting the person deployed, not you as a customer, and that's ambiguous, right? Which is something we have to figure out. What is that kind of expectation we need to have?
This is a gap.
Yes, yeah. Yeah. So auditing perhaps could address that. Again, I don't think the auditing literature is really tackled that level of certainty.
Let's see if the question from the audience abroad.
So it's just a quick question. Are you aware, there are so many domains where we have already rules and knowledge in form of ontologies or whatever. Are you aware of a project that make use of that?
I want to say yes, but I can't bring it up in my memory. So there are indeed, I can't quite remember the title of papers, but there are papers that try to harness, right? So I think there are things like counterfactual explanations in knowledge graphs, that kind of thing, right? Where you're harnessing existing ontological structures and things like that to come up with an explanation. And in fact, yeah, there is some discussion right now that if you think about issues like fairness and bias, you certainly need that kind of contextual understanding to have a more satisfactory, justification. Yeah, so I should be able to put it up, but I don't know it offhand. Yeah. Go ahead.
When you talk about causality, how do you relate this with reinforcement learning? You have so many techniques about causality.
Yeah, so yeah, obviously they are very closely related. I mean, I don't think I have something very definitive to say. So causal attribution in general is certainly one aspect in which an agent can get signals back from the environment, right? Or by acting, the agent can get feedback from the environment about what they've acted. So there is obviously a link there. And as you say, there's been a ton of work recently that has been looking at the interplay between causality and RL. I don't think I have anything concrete to say about that beyond what's being written out there. I would say that if there is, if the desire here is to learn, have some kind of causal understanding of the world, perhaps the RL framework is the way to go. But not everything necessarily provides the right kind of framework for that to play out, right? So in certain cases, it may not be possible for you to intervene. So, it might be dangerous or expensive or whatever. So if it's not in a simulation setting, it can be hard to really, have 1,000 epochs in the RL setting. So in those cases, perhaps we need something else.
All right, so I'll read a question from the audience, remote audience, but people say that it's being a bit hard to listen to the question, so I'll say from here. There's a question from Claude McMillan, it's actually the deputy director here in the center from IBM. He says, many recent human interface papers have shown little impact of explanations in improving user experience of trust. Do you know of studies which show that explainability is useful for end users? That's a great question. There.
All right.
There you go.
I don't think I know something off the back of my head on this. So the only thing I'm aware of is I think there's some work from Cambridge where they looked at deployment and explainability. But I can't quite remember if it was for end users. There's also work from IBM itself where they've looked at this thing called the IBM XAI 260 framework, where they have been arguing for us, analogous to what I said, that questions can drive explanations. They've been arguing for a kind of flow chart or a decision diagram kind of thing for connecting explanations to questions. And perhaps that's oriented for the end user, but I can't quite remember. So the question about trust is also, again, it opens up a can of worms, right? Because it goes back to like the question you asked about what does it mean if the user is not informed, or if the user doesn't have an understanding of how the model works, or et cetera, et cetera. So there are many dimensions to it. So I don't know if a trust itself is, we perhaps presume that explanations could be a prerequisite for trust, but we don't quite know exactly how it might work out, right? So there's also a study done at the Turing Institute where they looked at various stakeholders to try and understand the impact of explanations and what does it mean, like in the medical domain, if you have like 99.9% accuracy but no explanations versus 80% accuracy with lots of explanations or whatever, right? So I don't know. There's a conclusive result from that. So it still needs to be. I think it's an area that still needs to be probed a little bit more. And mainly the issue comes down to the fact that we don't have good quantitative understandings of things like trust and explanations. So as long as, and perhaps we never will, right? So, and that's the reason why people circle around the question with many proxy takes on it, right? And some of these are conclusive and some are not.
I think there's someone with a question.
I have a question, kind of similar.
You can say, you have to
Go there. Okay, already regret it. Yeah, so this is a kind of follow-up question. So most of these explainability frameworks that you show, they kind of work at the attribute level, so it's how they try to do like feature relevance or even assemble rules but out of the features or something like that. And in a way, I always feel that this is not really explained, because what does it mean to say that this pixel is relevant to a classification or this word, right? So I feel like the explainability at a human level should be about like properties or at least some more high-level features. And I don't know if you understand, but is this what you're trying to do with your method, perhaps? Because you're saying like with the whiskers, you can tell there is a cat because there is a like pointy ear or something like that.
Well, I mean, the first part of the talk didn't present in method. It was kind of laying out the landscape. I think what you're referring to is something that people are thinking about. So there's been a lot of work on so-called explanations by superpixels. There's been a kind of causal approach to explanations, where again, the idea is what would it mean if you changed counterfactually a region of the image? You would change the label, and if that's the case, could you connect it back to to what you're trying to identify. So there's been some work on that, and as I agree with you completely. So I think one thing we say in the paper as well is that if you don't have a good actionable feature space, it's very likely that your explanations are too coarse-grained for you to understand, right? That kind of makes sense. The question is whether we have a generic and rigorous way to connect these low-level pixels to high-level concepts. And my answer there would be to go back to the structured knowledge stuff, right? I think if you provided a nice link between the pixel approach and some kind of ontology or a more complex logical knowledge base, perhaps it's possible to then argue for an explanation at the level of the logical layer, which might make more sense than, as you say, pixels.
Yeah.
Makes sense.
All right, I think we've reached the limit that we have because we want to have Vaishak have some kajika that we have today. We have a special coffee to celebrate the Festa Juninas. People watching us they'll have to think about kanjika themselves. We have some 50 people watching, but and I see several questions. I saw several questions in the chat, but unfortunately we have to stop. Let me just say that this is another seminar, a special seminar. So thanks a lot, Vaishak, for coming, for visiting us. It's a special seminar in our series of seminars. We usually call these the seminars on perspectives in AI. I think this was an excellent perspective to have. And this will be in our YouTube channel soon enough. So thanks a lot, Vaishak. Thanks a lot, everyone.